Hello everyone, thanks for being here. I'm Ramesh Jha. I'm LANA lead for Agile BioFoundry. Our group is interested in high throughput screening of enzymes and microbes for functional improvement. Next. So enzyme engineering problem. I guess there is a huge combinatorial explosion as soon as you start to engineer any enzyme. So natural enzymes, they are suboptimal for industrial bioconversion and definitely inefficient on anthropogenic molecules, and many times we would like to actually improve their stability, catalytic efficiency, or reduce the product inhibition. And any method, be it like saturation mutagenesis, which is completely irrational, semi-rational, or even rational approaches, does not give you enough liberty to actually have very small number of designs if you want to actually improve that enzyme. And very soon, due to the combinatorial problem, you hit into millions of variants which needs to be tested. So when you look at this design, build, test, learn cycle through the lens of throughput, what you see is that there is no cap on design. You can create as many as you want. There is a soft or glass ceiling for build, and you can actually comfortably make like 10 to the power 6 variants of an enzyme or microbes in the lab. Test remains the bottleneck because most of the current methods can actually allow you to look at 100 or maybe 1,000 of different variants on a single day. And since learn depends on test, your learn is also compromised if you're not able to test lots and lots of variants. So our goal here is to actually have similar throughput for design, build, and test. Next. And how do we do that? For test, what we call a smart microbial cell technology, where we actually inside the cell create a gene circuit consisting of a transcription factor and a fluorescent reporter. And what this transcription factor do is detect the molecule of interest. It can be a central metabolite or metabolic intermediate or your end product. But the whole idea is that the efficiency of the one enzyme, which is actually making the product, or overall efficiency of the strain, which is leading to the production of your target molecule, that actually binds to this biosensor consisting of this transcription factor and results in production of this fluorescent reporter. So you are able to actually correlate the amount of product to the fluorescence, which can be easily visualized on, let's say, a Petri dish. The middle panel actually shows that where you have tens of thousands of these different colonies, each expressing different enzymes, and an improved version can be comfortably picked from that Petri dish based on the fluorescence. And you can always couple this to the high throughput format, which is using flow cytometry, where you can look at 10 to the power 8 cells per day. Next. So in Agile BioFoundry, in last 9 years, we have been able to apply this biosensor or develop biosensor and use it with flow cytometry for various purposes, such as enzyme engineering, where we actually went ahead and created a library and improved that enzyme for reduced product inhibition. On the right side is that we have been able to actually look at adaptive laboratory evolution, evolved population, and based on the fluorescence, we could actually select the good producer from just the good growers. We have adapted this technology to different organisms, non-model organisms, Pseudomonas putida, Corynebacterium glutamicum, Acinetobacter baedeii ADP1, and we have developed this biosensor for different target molecules such as muconic acid, TPA, beta-ketoadipic acid, and adipic acid. And some of these beachhead molecules are metabolic intermediates such as PCA, pyruvic acid, and corysmic acid. And depending on what you exactly want, we are able to actually tune these biosensors to have different sensitivities so that it is good for a given microbial strain and for their production efficiency. Next. So this is an example where we actually created a muconoid biosensor, and using a diversification of the native promoter of this CAT-M transcription factor, we were able to actually adapt it to Pseudomonas putida, which is of our interest for muconoid production. And we show you in the middle panel that there was a high response with some of these precursors for muconic acids such as PCA, benzoate, and catechol. And we introduced this biosensor to an ALE population and performed FACS and chose this bright population, which would mean that they are not only good growers, but they are also producing your molecule of interest at high titers. And using this, we were able to actually get few variants which had multiple mutations, deletions affecting sugar regulation, and ultimately some of those mutations were kind of introduced into the original strain to get twofold increase in productivity. Next. So we have further gone ahead and challenged this particular approach by looking at two certainly different strains. Both can be good producer, but then a couple of mutations away from each other, which gives them some advantage in terms of growth or productivity. And here we give you an example of GB62 and GB271, which shows some difference in productivity, but they are only two mutations apart from each other. So we started with a mix of these two different strains at a ratio of 1 to 5,000. The rare one is actually a good producer. And in 2 rounds of FACS, we were able to enrich that good producer by 16-fold, and ultimately we had a ratio of 1 to 225. So basically what it says is that this particular kind of, tool can be used for something like RBT and seq library, which Alisa just mentioned, where each variant is expected to be away from different variant by, let's say, 2 deletions. So we are very hopeful that this particular approach is kind of, adaptable to some of those genome scale libraries. Next. And then one more thing I want to add is that thermostability remains a very critical aspect of any enzyme, and we have one of the previous presentation mentioned that we are actually interested in some of these thermophiles for consolidated bioprocessing. But what I want to bring here is that most of the thermostabilization work has been performed in mesophiles, and many of those proteins are not transferable to these thermophiles. So what we want to do is, we want to actually come up with a method where we do screening of these enzymes for thermostability in a thermophile itself. And for that, we are going to actually, come up with certain kind of, fluorescence-based method, which I'm going to describe in my next slide. Next. So we need a fluorescent reporter for sure. There is actually, most of the thermophiles are also anaerobes. So basically, we want an anaerobic reporter. And the idea here is that if you have an anaerobic reporter, it can be used as a reporter for enzymatic activity for a biosensor, but you can also fuse that reporter to certain enzyme. And if that enzyme expresses, then you get a fluorescence. If it does not express, the fluorescence is quenched. So basically, we use this YFAST as a starting point and constructed a library of around 18,000 different variants in a thermophile called para-geovacillus thermoglucosidaceous. And this was made possible by actually having an intermediate step of methylating the plasmid library using a strain that was developed at Oak Ridge in Adam West's lab. Next. And when we actually display the library on Petri dish, on the left is actually native YFAST expressing colonies, and you see that they are more or less kind of, dull or dim. But the YFAST library, which was actually, which has several mutations, when actually grown at 55 degrees Celsius, we see several of these colonies which stood out. And we ultimately found a few of those variants with 6 to 9 mutations for substantial gain in stability, and most of those kind of mutations were actually improving the polar interaction or improving the rigidity of the loop. Next. And in a second round, we used another method to actually create a more focused library around one of the improved versions from our previous cycle, and 2,000 different variants were actually created. And from there, again, based on the fluorescence on the Petri dish, but now at 68 degrees. Our previous experiment was done at 55, So at 68 degrees, we were able to pick up some colonies which showed improved fluorescence there, and we went ahead and actually produced those proteins. And what I show you here in the middle panel is that 3 different variants starting from YFast, TS-Fast, and TS-Fast 2.0, which ultimately increased in thermal melt temperature from 46 degrees to 57 and ultimately 66. And again, we saw some kind of very interesting mutations, which was more to do with space filling or coming up with new salt bridges. So with some of these reporters being produced, what is the next step? We want to use it as a protein folding reporter for screening the thermostability of enzymes. And here in one example, I show you these 2 different reporters, the native and one of these improved version, TS-Fast, and 2 enzymes. Both are actually the petases coming from mesophile as well as thermophile. So we have 4 different combinations, and at 37 degrees, when you go ahead and express these fusions, all of them are actually more or less fluorescent. But at 55 degrees, only one variant, which is actually thermophilic enzyme, fused to a thermostable reporter, stands out there. And we can still see the fluorescence at as high as 70 degrees Celsius. So basically, the engineered TS-Fast functions as a protein folding reporter at high temperatures, and we are very much interested to use this particular approach to diversify the enzyme of interest and screen them for thermostability at high temperature. That was my final slide. Thank you for your attention.